So I heard my husband and my son arguing in the bathroom over and over until they decided that they were going to have this bet. And while I was listening to it, before the end of their conversation, I had ordered a pressure sensor off of Amazon, which arrived the next day. I have an Arduino Uno connected to ground, 5-volt power, and A0 for data. I have a resistor connected and a pressure sensor connected. For some reason, my son decided that using his foot to put down the toilet seat was a good idea. And he would not hear anything about us telling him that it wasn't and that we were concerned that he might break the toilet. But what can you do when your kid just won't listen to you? An Arduino and a pressure sensor came to the parenting rescue this week.
Hey Mom, what's an Arduino?
An Arduino is a microcontroller. You plug it into your computer, you write C-based code, and you can control things like sensors. You'll compile it, and then you'll upload it onto the Arduino from the computer, and then you can run things.
I didn't understand much of that. I don't understand much computer stuff.
Yeah, well, we're going to go a little bit deeper into that, so don't worry about that. So you think it's better to use your foot to bring down the toilet seat? Or bring up
it's better.
You know it's better. And Baba knows that it's better to use your hand because you have more control with your hand. So how do we get past this argument? My husband's going to close the toilet seat 100 times with his hand. My son is going to close the toilet seat 100 times with his foot. And we're going to measure each time, and ultimately we're going to take the average of the output of each, compare the two, whoever has the lowest wins. Now what happens when you win?
I get $10, Baba. That's to take 10 toys.
And that helps us out because we're moving. So moving less is helpful. We're going to donate them. Are we an odd family? Like, does anyone else do this? Use a microcontroller to prove their point to their kid that doesn't believe you? So the sensor I ordered off Amazon was a thin film pressure sensor. And the first thing you do when you're working with a new sensor is you want to learn how it works. So when I did some reading, I learned it uses the piezoelectric effect, which is where material creates an electric charge in response to the stress, and the force of the pressure generates an output signal corresponding to the magnitude of the pressure. So basically the pressure that's being put down on the pressure sensor, it'll be read into the Arduino, and the Arduino is able to tell me that magnitude of pressure. And I can write an algorithm that can then handle that, take in each of the max values of pressure at each iteration when the toilet seat's put down. And then I want to take an average because, yeah, I could write an algorithm where you just get the brute force max value and rerun it every time, but I have a computer to be able to take each one and calculate the average. So that's what I want to do. Next, we're going to explore the capabilities of the sensor. So I'm going to write a quick program just to stream in the sensor information and learn what is the min and max value of the sensor and kind of get a feel, as I push down on it, what output do I get? The first thing you notice when you open an Arduino IDE is that you have two functions. One is the setup, which runs one time, right when you start the program, and the other is the loop, which runs over and over again unless you put something in that breaks it. So here's our simple program, and we need to make sure that we're connected to our board and the right port. So in our setup, which runs once, we start with a serial.begin, which opens up a serial communication using 9600 as the baud rate. And that's basically the number of times the signal can change over a second. And what's important is it needs to make sure that the baud rate in the Arduino IDE on the laptop is the same as the baud rate on the Arduino. And that allows communication to flow so that we can later print the data that we're reading in. Then we set the pin mode, so we're setting A0, which is what I have physically connected on my Arduino to the pressure sensor, as input value, so we can read in the data. And then in our loop, which happens over and over and over again, we're going to go ahead and print the data that we're reading in with analog read A0, so the A0 value that we're reading in, which is the pressure value that we're reading from the pressure sensor. Next, we'll compile and then load it onto the board. And we can come over here and see the output as it's streaming. And you can see when I push on the pressure sensor, then the values that are streaming go up. So you can see the pressure readings. And I found that the min and max value is 0 and 1023. What I should have done was also create an algorithm that can measure the hertz rate, or the rate of the return that I'm getting from the sensor. I think I didn't do that because I'm so used to running with autonomous systems, working with sensors like radar, camera, LiDAR, where they come back at like 10 hertz. But there's a lot of other systems that run at different hertz rates, like medical device systems that run at 100 hertz, like 100 times per second. Because they're very critical systems, you need returns often and frequent. There's also IMU that runs very quickly. You need to take in each of the change in returns so that you can have a very accurate representation of your position of your robot. And it's a lot smaller amount of data that you're taking in, right? Single integer or float values that are coming in. When working with LiDAR and radar, that's just a burst of a ton of data that you have to process 10 times a second, so you probably couldn't even run faster than that if you wanted to. So not measuring the hertz rate ends up biting me later, but we'll get to that. Next, we want to understand the limitations. So with some sensors, like LiDAR, you can't get a return off of glass, and that can be a huge problem. But with the sensor is fairly simple. It's a pressure sensor. The only thing I really found of value is that it doesn't get hurt if you put a pressure over the max pressure value. You also want to get a feel for the flow and tendency of your data that's coming in. So if you start playing with the sensor in like the real environment that you're going to be working with it in, you'll learn things. Like what I learned is there's kind of a phantom value that'll sometimes be produced when I'm not even touching the pressure sensor. So values oftentimes below 20 or 30, but occasionally they creeped up to like in the 70s. So I went ahead and put a threshold at 100 where I knew in the algorithm I would need to add a filter so that no values under 100 would be considered a real pressure value when they're putting down the toilet seat, so that it wouldn't skew the results to benefit somebody in having a lower average value. Next, let's talk about the algorithm. So we're going to get a series of return values from the pressure sensor. Most are going to be 0 when the toilet seat's up, but we're going to get a few of the phantom values, which we'll go ahead and filter out so we have all zeros. Next, we're going to do our first iteration of closing the toilet seat. And on an easy return, we're going to get a single value. So we take that and we add it as the first iteration. On other returns, we may get a series of values. So we're going to take the max out of those series, add that as the next iteration. We keep doing this, take the max until we've done it 100 times. And then eventually we have our 100 iterations, and we're going to go ahead and take the average out of all of those, which is the end result. And with every algorithm, we have data structures. The first one we're going to use is a queue. That's FIFO, first in, first out. It's like a line of people. So the first person in the queue is going to be the first person that gets served or popped off the queue. The last one in the queue is going to be the last person that gets served after every other person in line gets served. So we're going to use this for our data stream. Each data coming in gets pushed onto the queue. And we do this because we can't possibly store an endless stream of data, or else eventually the computer would crash and burn. So we set a size for our queue and we delete all of the oldest data as it comes in beyond that size. The next we're going to use is an array. So because we know each person's going to do 100 iterations, we can set the size of our array to 100. And as each iteration comes in, we store each value within the iteration. And eventually we take that and we take the average of all of the iterations we've gone. And the lower of the two averages is what wins. Now it's time to dive into the code. So first we include our libraries, and this is where I start missing C++, where you get the standard library and all of the data structures that are included with it. On the Arduino, it's a more constrained system, so you have to manually import and install each of the libraries that you need. We're going to go in and manually install the circular queue because we need to use the queue. Next, let's go into the global variables, which I could have made as static variables in the loop function, but I made them global variables. So the const variables, we have the pressure count, which is the number of iterations. We're going to put down the toilet seat and get the max pressure for each time, so that's 100. Next, we have the zero break count, and that's the number of zeros in a row that needs to be together before we consider it a break, or when we open up the toilet seat. Next, we have the above min value, which is the threshold we use for filtering out the phantom variables. So basically anything between 1 and 100, we're going to consider that's not actually a real pressure that we are going to consider. Next, we're going to create our data structures. So we have the max vals int array based on the size of the pressure count, because we're going to be storing 100 max values each time the toilet seat is lowered down. Then we create the queue, and that's an int queue with the size of 0 break count, and that's going to be the data that's flowing in from the pressure sensor. And it's the size of 0 break count because the next variable is the queue sum. We're maintaining the sum of that queue so that when the total sum, the size of 0 break count, is all 0, we know that we have a break. Next, we have the array index, and that's going to keep track of where we are as far as putting the max values of the pressure into the array. Then we have the max val, so we're updating that each time we have the toilet seat going down. And then we have a boolean, which is during break, We set that to false. We're going to be updating that as we go. Then we have the setup function where we set up the serial communication with a baud rate of 9600, just like we did before, and set the pin mode of A0 to input so we could read the data in. Then we have our loop function, so we're going to be reading in the sensor value from A0, and if the sensor value is in that phantom variable threshold, then we're just going to return early. That's how we filter it out. Next, we're going to update the queue. So if we're at the max size of the queue, we pop the latest, oldest variable off the queue, and we remove that value from the sum so that we can maintain the sum value of the whole queue. Then we go ahead and push the new data onto the queue and update the sum with the new data. We update if this variable is greater than the max value, update the max value, and then we use the ternary operator to update whether we're on a new break or not based on whether the queue sum is 0. Then we check, and if we're not already in a break and it's a new break, then we check the max value. We add it onto the queue, we print it out, and we increment the array index so that next time we record the max value, it'll be at the next array index. Then we check if the array index is at the pressure count, which means we've already recorded all 100 values, and then we go ahead and calculate out the average if we are at 100 values and print it out. I added an extra delay because the program was ending before it could actually print it out, so that ensures it prints it out before we get to the very end. And that's it. So, are you excited to do this bet?
Correct.
So something unexpected happened when running the test. When my son ran the test with his foot, he was very inconsistent with kind of the putting down and the coming up. It's almost like he created this ripple effect. And you can see it in the data if you know what you're looking for. Initially it looks like gibberish, but then you start seeing the patterns of the data trending downward for each iteration. And what I think is happening is when my son brings his foot down, he has the initial large hit, and then as he kind of tries to wiggle and jiggle his toes out, it has ripple effects where the pressure sensor kind of hits gently as his toe comes out. I mean, this is why we're doing the test, is because we know it's inconsistent and we know it would likely produce a worse outcome overall. It makes it interesting because you need to make sure that the results and values coming in are actually representative of what's happening in the test. I think because it ran at a faster hertz rate, we were getting a lot of returns very quickly. If it runs too quick and we don't have enough zeros in the break value, we're just going to record too many max values. And this is where it ended up biting me. And so I finally ended up writing that program that I should have written in the first place to be able to calculate how many times we're running the loop each second. So first I set my end time and the loop count, and inside of the setup I set the end time to 1 second later than now. And then in the loop, if it hasn't hit 1 second later, then I just increment the loop count. Otherwise, if it's hit the 1 second later, I print it out, reset the loop count, and reset the end time to 1 second later than now again. I was able to get this to run. Sometimes it fluctuates a little bit, but what I found was it was running at like 5,700 hertz. That's 5,700 times in a second. I was assuming 18. Doing the calculation, 18 over 5,700, that basically meant that I was assuming a break for 0.003 seconds. That blew my mind. Interestingly, in 0.003 seconds, about 10 tons of water falls over Niagara Falls. The universe expands about 44 meters, and $182 is spent around the world on military. But that's beside the point. It isn't nearly long enough to be considered a break for this test. At the end of it, though, what I had considered and what I had seen is basically for each iteration that my son was running it, the highest value was being represented. He had several other low values surrounding his high values. So the average overall would be much lower than what the average of actually the high value for each iteration would be. So logically, if my husband produced an average low value that was lower than his average, then my husband would still win because my son had more of a biased average lower than what he should have gotten. And I think that's a fair conclusion. So now my husband's gonna go.
And with an average of 338.75, we have a clear winner. So much of the data is so close together you can't even read it. It's very consistent. So let's take a quick look between the two data sets. The first thing we note is the highest values for Nelson's were in the 8 and 900s. The highest for my husband's were at 495 and 522 right at the beginning when he was starting to get used to it. Those are the only values that were actually larger than Nelson's average of 449.54. So I think we have a clear winner.
And that is toy number 1 that is going away. So it seems the traits that make kids so frustrating to parents can also be the same traits that end up being their greatest assets when they become adults. So my kid being, very stubborn, doing things differently, maybe those will contribute to him doing something great like figuring out a cure for cancer or figuring out a new method of travel or creating a new renewable energy source. Who knows? But I wish him luck. I really enjoyed making this, so if you enjoyed it too, consider liking and subscribing, and we'll see you next time. So, are you excited to do this bet?
Correct.
Are you excited to learn the code that we use for doing this bet?
No.